In this video, we move from slow event-related designs to fast event-related designs, which have a number of advantages compared to slow event-related designs. So we saw in a previous video that Buckner et al. Showed that responses to single events could be obtained and can be compared to those of a block design. So we get maybe not the same magnitude of responses using these types of single events, but we can extract the hemodynamic response to a single event by signal averaging, basically. And we can get responses to single events that at least allow us to do statistical tests on these that are somewhat similar to those of blocked responses, but not with the same magnitude of detection power. This here is showing the time series, well, an example time series from a slow event-related design. And obviously what's obvious from this is that what we're doing here, we're allowing the hemodynamic response to return to baseline before we present a new stimulus. So that the stimuli are indicated, so when the stimuli are presented are indicated by these white lines here. And you can see that the response returns back to baseline before a new stimulus is presented, at least on most cases, right? Such as here. So we go back to baseline, then we present a new stimulus, and we can see that there's a new hemodynamic response that returns back to baseline. So this allows us to then extract the hemodynamic response via signal averaging for all these trials. And it has been shown to be comparable to the results of block designs in a sense, although with lower detection power. Now, what we want to ask here is what happens when stimuli are presented in rapid succession. So before the hemodynamic response to the previous stimulus goes back to baseline. And this has a number of advantages, one of them being that we can present more events to participants than in a slow event-related design. Another one is that the experiment is much more interesting to participants and they don't get bored and tired as quickly. What we have to consider here is, however, how these two events, how the hemodynamic response to two events in rapid succession combines. Does it combine linearly, which would be advantageous because then under the assumption of linearity, we can basically extract the hemodynamic response to the second event by subtracting the first event, or does it combine non-linearly? And obviously this is important because it allows us to determine whether responses are superimposed. So basically using subtraction to identify the first event, the hemodynamic response to the first event. And this is basically how this would look like. So let's consider a very simple experiment again, in which a word is presented and then followed by a second word in a 5-second delay, and the task of the subject could be, for instance, is the first word the same as the second word? And so there is a bit of a working memory demand here, which is you have to keep the first word in mind for about 5 seconds. So we're asking most of the regions then that respond to the first word actually should also respond to the second word. For instance, visual regions that are involved in encoding letters, and regions that are involved in understanding the meaning of the word. So we would actually expect regions that respond to the first word to also respond to the second word. And we want to ask, how would a hemodynamic response look like? If we have superposition, such as shown here, so this is this bar here indicates the presentation of the first word, the second bar indicates the presentation of the second word, and these are the individual hemodynamic responses, one in blue, one in red. If we have superposition, then we would expect a response like this. So the bold response to the first word goes up and then somewhat decreases, but then it starts adding. So you get this little bit of a dip here. Then it starts adding jointly with the increasing hemodynamic response in response to the second word. So under the assumption of superposition, we would then be able to distinguish between regions that respond to the first word only, to the second word only, or to both words. So we can create these models of the responses under the two scenarios, right? Obviously, we would observe only the first response if they respond to the first word only the second response if they respond to the second word only. But this combination response based on superposition, so if the region is active to both words, then we would observe this type of response that is based on a combination of these two types of responses that I described earlier, namely this superposition. So whether superposition occurs is crucial for analyzing fMRI data that is fast event related. And the key property of a linear system is that the joint response that's shown down here should be, if it's linear, a simple addition of the response to a first event and the response to a second event. So the function of A is the blue line here, and the function of B is the red line here. And then the joint response, function of A plus B, is then this superposed or this purple response here. This is if it's in the case of linearity. In the case of nonlinearity, what we might have is that a region has somewhat of a refractory period. So it shows it has a somewhat diminished response to the second word that is shown, leading to some form of suppression, which we actually do find in some cases. It's called attenuation or repetition suppression, which might occur. So we do know that there are some nonlinearities in the brain, but mostly we find actually that it's linear, and I'll show you an example of this later. And we can actually test this, right? We can test whether some regions respond linearly or non-linearly by looking at the bold response to stimuli that have been presented in repetitions. Another key property of a linear system is scaling. And this is something that you may have encountered before when, for instance, we talk about parametric modulators. So that means basically that the magnitude of the stimulus that is shown, if it increases in intensity, then the bold response, the bold signal, should also follow that intensity. So if a stimulus is twice as large, then we should observe a bold response that in magnitude also that is twice as large, or maybe even 3 times as large. And this is one thing that we obviously use in neuroeconomics quite commonly when we have a model parameter or a subjective value parameter that allows us to track the magnitude of the bold response in response to increasing or economic value that is increasing or decreasing across different trials, for instance. Now, so the linearity has been studied by, an interesting study by Dale and Buckner in '97. So this is something that dates back quite a bit to the late 90s. And basically their study demonstrated that it's feasible to do faster event-related designs. Here's what they did. So they presented single events in isolation and compared the responses to an estimated response of events presented in close succession. So we're looking at events that were presented in clusters of either 1, so that's basically what we know from slow event-related designs, but then also 2 or 3 stimuli that were presented in rapid succession, and they used 2 intervals, one with 2 seconds and one with 5 seconds. But let's consider the ones with 5 seconds first. So what should happen is, if you have 2 or 3 stimuli presented in rapid succession with only a 2-second gap in between, then the responses should be identical. And you should be able to subtract, to recover the responses to the second stimulus by simply subtracting the first stimulus, and the response to the third stimulus by simply subtracting the response to 2 stimuli. Right? I'll just demonstrate this in a second to make this clear. So we already know slow event-related designs. They basically present one stimulus for a certain period of time, such as 1 second for this checkerboard here, and then there's a kind of a long waiting period before the next stimulus is presented. 20 seconds, such as in this study, are more than sufficient for this. And this allows us to look at a hemodynamic response to this event presented here at this time point 0. Then we see there's a rise to the threshold, or to the peak amplitude at about 5 to 6 seconds, and then there's a slow decline again, and at about, well, actually here in this case at about 12, 13 seconds, participants are back to, or the bolt response is back to baseline. Now, what happens if we present two stimuli in rapid succession? If we have superposition, then the response to the first one should be added, or the response to the second one should be added to the response to the first one, right? And that's exactly what we're seeing here. So we have this initial response, then a bit of a decline, and a second response that leads to a bit of a larger peak. So the amplitude goes up a little bit more. And as you can already imagine, you should be able to get the exact response to the second, the bolt signal to the second stimulus by simply subtracting the bolt signal of the first, of just the one event from this signal, right? So you should be able to recover this red line here by subtracting the blue line from this joint response function here. That's exactly what the experimenters did. So they took the slow event-related response from which occurred on a subset of their trials, and then subtracted the single event response, which is shown here. So it's just the hemodynamic response to one single event from this joint superimposed hemodynamic response. And what they find is that there is a large overlap. So this is the first trial response. It's exactly the one that's shown on the right side of this figure. And this is the estimated second trial response, which is taking this figure and subtracting this bolt response from it. So you get about the same response, maybe with a bit of a steeper decline, but that could just be some measurement error here. So it's a very similar response, basically giving an initial indication that that the bolt response is a linear system, so that the addition of two, or the presentation of two stimuli, leads to a hemodynamic response. That's simply the addition of the response to the first and the response to the second stimulus. Now we can also move on and look at presentations of three stimuli in rapid succession. And what we see there is that we can still do this. So subtracting the, in this case, a three stimulus response is our baseline, and then we're subtracting the two stimulus response from it. So it's a similar approach to this, but on the left side of the figure we have a response to three, not two stimuli. On the right side of the figure we have a bolt response to two, not one stimuli. And that's exactly what's shown here. So this is the raw data. This is a one trial event, this is a two trial event, and this is a three trial event. So we are here subtracting the red line from the black line. So the two trial event from the three trial event. And you can see that, again, the estimated third trial also falls in about the same range of the estimated first and second trials. You can also see this is based on the 2-second delay condition versus the 5-second delay condition, which shows somewhat better data. But you can also see from so in a 5-second condition, we have a better match between the blue, red, and black lines. In a 2-second delay condition, we have a somewhat worse match. So it also depends on, so how well this linearity works depends on the type of timing that you use, which is something you should consider when you design your event-related experiments. So let's summarize this. If it comes to linearity and single events, responses to the second stimulus were obtained by subtracting the single stimulus response from the two stimulus response. The same was true for the third stimulus, which are obtained by subtracting the two stimulus response from the three stimulus response, just as I illustrated earlier. And in the linear system, responses should be identical in a perfectly linear system. Now we find responses that are not entirely identical, especially in the 5-second case. They're very closely matched, But in the 2-second case, so when gaps between stimuli were only 2 seconds, not 5 seconds, they were not as closely matched. But still, there's a rough match between these. So what does this mean? Both responses add in a roughly linear fashion, basically. So finally, to illustrate some of the advantages of fast event-related designs, here's an experiment by Dale and Buckner again in 1997. And they conducted, as you can see, a lot of experiments on what's possible within the fMRI environment, and especially when it comes to event-related designs. So what they did here is they presented these checkerboards again to participants, once in the left visual field, once in the right visual field. And as you might remember, presenting something in the left visual field activates neurons in the right visual cortex. So they did this. They randomized when they presented these checkerboards, which were presented for about 1 second, and then they had a 2-second, a 5-second, or a 10-second intertrial interval. And together with random presentation, well, it turns actually out that having just a 2-second interval leads to the largest activation relative to, well, especially the 10-second interval. The reason for this is that you have a lot more trials to work with in a 2-second period. So when you average the signal, you end up with better signal in the end. So having a larger number of trials is something that is advantageous for both signal, but also for statistical maps. Especially compared to something that is slower here. This is almost a slow event-related design where you have a much lower extent of activation and much lower p-values. So this is an illustration that fast event-related design, under specific circumstances, namely when stimuli are randomized, can have advantages, also in terms of detection power. So finally, to illustrate some of the advantages of fast event-related designs, here's an experiment by Dale and Buckner again in 1997. And they conducted, as you can see, a lot of experiments on what's possible within the fMRI environment, and especially when it comes to event-related designs. So what they did here is they presented these checkerboards again to participants, once in the left visual field, once in the right visual field. And as you might remember, presenting something in the left visual field activates neurons in the right visual cortex. So they did this. They randomized when they presented these checkerboards, which were presented for about 1 second, and then they had a 2-second, a 5-second, or a 10-second intertrial interval. And together with random presentation, well, it turns actually out that having just a 2-second interval leads to the largest activation relative to, well, especially the 10-second interval. The reason for this is that you have a lot more trials to work with in a 2-second period. So when you average the signal, you end up with better signal in the end. So having a larger number of trials is something that is advantageous for a bold signal, but also for statistical maps, especially compared to something that is slower. Here, this is almost a slow event-related design where you have a much lower extent of activation and much lower p-values. So this is an illustration that fast event-related design, under specific circumstances, namely when stimuli are randomized, can have advantages, also in terms of detection power.